Do you feel the vibes?
We started talking about how to find slope of a curve at a specific point. Okay, so when you do that, you're literally just finding the rate of change just at that one point. The rate of change just at that one point. Okay, so imagine you go on a road trip, right? Let's say I don't know, like 300 miles, okay? And it takes you 5 hours to get there. What would have been your average speed? 300 miles, 5 hours, what would have been your average speed? And you know this. 300 miles. 60 miles an hour. Okay, it's a Monday morning. Now, that's your average speed, right? It's the average rate of change of you going from here to that destination. But were you going 60 miles an hour at every single point in time? No. Sometimes you were going 40, sometimes you were going 70, sometimes, right? But, so your speedometer was recording different things at every point in time. So at a certain point, if you happen to look at your speedometer, whatever that reads, right? So suppose it reads like 67 miles per hour. That is your rate of change at that particular moment. So if you were to graph your trajectory, that would be the slope at that one particular time. So when we have been finding slope at one point, we're really looking at what your speed would be on your speedometer at a given point in time. Okay? So right now, though, we're going to talk about average rate of change, which is the total distance. If we're talking about, distance, it's the total distance traveled divided by the total time. We've actually done this in chapter 1, okay? So the average rate of change is f of b minus f of a over b minus a, okay? So when I have a function, right? Suppose I have a function like this, and this is a, and this is b, okay? F of A is this point. F of B is this point. So in going from A to B, the y values here changed, right? When you want to find the average rate of change, right? You want to see, like, on average, how much did this change? Okay, or what was the rate that this was changing? Okay? So that's F of B minus F of A over B minus A. The only time you use that is literally if you're looking for average rate of change. I mean, it's like very straightforward. Okay. So let's talk about velocity, right? Because many things change, but when we talk about like distance and velocity, it's always more like applicable. Better stay with me, buddy. Okay. Huh? Okay. All right. Okay. So average velocity is the total change in distance divided by the total time it took, okay? So what is your total change in distance? That is called your displacement. Now, displacement is not only how much has your position changed, but also in what direction has your position changed, right? So for example, if like something starts, at a point, and then, it keeps going like back and forth, at the end of the time, if it, let's say, landed 10 meters to the right, that's displacement. If it landed 10 meters to the left, that would be negative 10. That's its displacement. So displacement over time is average velocity. Usually, position is given to us as s of t. So the final position, s of t2, that's the final, minus the initial position, s of t1, over t2 minus t1, that's your average velocity. Okay, so let's take a look at this. A water balloon is propelled straight up using a launcher. The height of the balloon in feet, t seconds after it is launched, can be defined by this. So the height is given in feet, and then, t seconds after. So those are the units. Can be expressed by this. So d now, it's d of t, that's the distance. What was the balloon's average velocity between t equals 1 and t equals 2 seconds? So basically, if you want the average velocity, it's going to be d of 2 minus d of 1 second over 2 minus 1. How do you find d of 2? You literally plug 2 into the function, and magically you get 71. Then you plug 1, you get 54 over 1, and you get 17 for your value. Okay, so 17. So that means the average velocity was 17 feet per second. Now, that's all you need to write. But notice, when you do this, the sign is positive. That, it gives direction. Okay? Velocity, acceleration, displacement are vector quantities. They're vectors. So the plus or minus, it gives direction. Okay. So that's average velocity. Instantaneous velocity is the velocity at a specific point. Literally, like if you look at your speedometer at a given point, how fast are you going? Okay? To find instantaneous velocity, it's the limit of, that secant line like we were doing before. Okay. So, here we go. A window washer accidentally drops his lunch off his scaffold. I know, it says, I always want to change this, so, because I feel bad for the window washer. But it's okay. It's okay. Huh? What are you doing, walking under a scaffold? See, that's what you get. Right? But it's okay. There is a second part to this, and his friend actually shares his lunch with him, so it's okay. So a window washer accidentally drops his lunch off his scaffold 1,400 feet above the ground. The position is given by this, where time is given in seconds and the position is in feet. Find the instantaneous velocity, okay, of the lunch at t equals 7 seconds. So v of t, the instantaneous velocity, is going to be the limit as h approaches 0, d of t plus h minus d of t over h. So this is the limit as h approaches 0, 1,400 minus 16 t plus h squared, right? Minus 1,400 minus 16t squared in parentheses. Everybody okay with this? I'll take that as a yes. Okay, so simplify this. Limit as h approaches 0, 1,400 minus, I'm just going to give you the simplified version. So this is 16t squared minus 32th minus 16h squared minus 1,400 plus 16t squared over h. Okay, positive 1,400, negative 1,400. Negative 16t, positive 16t squared goes away. So again, your second, f of x or d of t or whatever, should all cancel. So now we can factor out some h's. And we get negative 32t minus 16h over 8. These cancel. Now I can plug h as 0 into the function. So what do I get? Negative 32t. That's the velocity. Okay. Now, but what I want is v of t at 7 seconds. So v of 7 is negative 32 times 7, negative 224 feet per second. And of course it's negative because this, poor guy's lunch is going downward. Yep. Okay. Huh? It's a fast lunch. You don't want to be standing under it. So, moral of the story, don't go walking under scaffolds because somebody's lunch could be falling. Now, if it was in like one of those like aluminum lunch boxes, I mean, that's not cool. Yeah. Mm-hmm. Oh my. Okay. The distance in feet, oh, this should say in feet, of a water rocket from the ground after t seconds is given by this. Find the expression for the instantaneous velocity v of t of the rocket at a time t. Okay, I'm going to give you guys a minute and a half to do this, right? So you're going to do v of t is equal to the limit as h approaches 0, s of t plus h minus s of t over h. Okay, you have a minute and a half. On your mark, get set, go. So v of t is 90 minus 32t. Right? So make sure you can just like do that beginning to end. If you have issues, come see me. But like, okay? All right. Given the position function where position is expressed in units of meters, find the average velocity and then the instantaneous velocity. Okay, so average velocity yeah, it's exactly what it is. It's because it's how much it changed over time, right? The total distance over the total distance over the total time. Okay, um so this is x of 5 minus x of 1 over 5 minus 1. Notice the notation here. You have to show me this notation, right? As like your work. Because if we also move from here to calculus, then notation is very, very important. So make sure you show all that. So now, after you do that, you can just plug in, and then you can say 75 minus 3 over 4. This is 18. And, it's meters per second. Okay, Ben, you had a question? Oh, so here, okay, we have to find the instantaneous velocity at 4. Now, remember last time I had shown you guys two ways of doing this, method 1 and method 2. I'm actually going to do this using method 2 today, just to give you guys a little bit more practice with it. So now we want to find v of 4. We want to find the velocity at t equals 4. This is going to be the limit as h approaches 0. Oops. So look, it's x of t plus h, correct? So it's going to be x of 4 plus h minus x of 4 over h. Okay? So remember, it would have been x of t plus h minus x of t, but t is 4. So here, this is the limit as h approaches 0. What's x of 4 plus h? It's 3 times 4 plus h squared minus 3 times 4 squared over h. Huh? Yeah. So, okay, so you know what? Let me do some work here. So this is going to be 3 times 16 plus 8h plus h squared. So that's going to be 48 plus 24 h plus 3h squared minus 48. Everybody with me? Yeah, everybody with me so far? Over h? Okay, see again, it's like magic. The 48s will cancel. So we have the limit as h approaches 0. Factor out an h. 24 plus 3h over h. Those go away. So I just have 24. And then do we have units here? 24 meters per second. So the average velocity of this was 18. But at t equals 4, if you tracked it, it was going at 24 meters per second. Huh? What 3? The 3 is part of the function. Yeah. Okay. Okay. I have literally like gone through like all of Macbeth this year from like the other side of the wall. Okay. When an object is thrown straight down, the total distance the object falls can be modeled by this. Okay. Where t is measured in seconds and the initial velocity v naught is measured in feet per second. If an object thrown straight down from a height of 816 feet takes 6 seconds to hit the ground, what was the initial velocity of the object? Okay, so let's go ahead and do this. So y is equal to 16t squared plus v naught t. Okay, so we want the initial velocity of the object. The initial velocity is v naught. That's what we're solving for. And then the height is 816. So we put in 816 equal to 16 t squared plus, what was the t squared? 6 squared plus v naught times 6. Okay, can somebody plug that into their calculator? Tell me what was the average velocity of the object? So now the average is equal to the final position minus the initial position. So 0 minus 816 over 6. Okay? Negative. Huh? Because that's how long it took. So the displacement minus over the total time. Right? Total distance over total time. Okay? All right.
Press start.